Welcome back everyone, Patrick here, and moving on to another example dealing with the intermediate value theorem. Very similar example to the ones we did before. If you didn't watch those, make sure you do, and the overview video, just because I go through the process perhaps in more detail than I'm going to go over in this example. I'm going to assume that you've watched those videos, so I may go through this a little bit quicker. And notice that the format of this question is the exact same as the previous two examples. We got to show this equation here has at least one real root, meaning that there's an x value that's going to make this left side, x minus 5 to the power of 3, equal to this right side, 2 sine of x plus 1. So first step, like we did in the previous examples, you want to bring everything over to one side. So I'm going to take this 2 sine of x plus 1, I'm going to bring it over, so I'll have x minus 5 to the power of 3 minus 2 sine of x plus 1. And that's going to equal 0. And so what we want to do is we want to define a function on this. This is the function we're going to be working with, the expression on the left side. So f of x is going to equal x minus 5 to the power of 3 minus 2 sine of x plus 1. And we basically have to show when does this function equal 0. Or rather, we don't have to show when it does, we have to show that there's going to be some kind of x value that's going to make the function equal to 0. We have to show that this function is going to have at least one x-intercept. Because if we show that this function has at least one x-intercept, or we show that this left side can be 0, then we're basically showing that up here, this left side can equal that right side. So, like I did in the previous example as well, what I want to do first is talk about the domain of this function, or the continuity of it, just because when we use this theorem, we got to make sure that we're picking an interval where the function is going to be continuous. And luckily, if you look at this function here, there's actually no restrictions on x. Notice that this expression, x minus 5 to the power of 3, that's continuous. The domain of that is XCR. You could plug in any x value into this expression, and you're not going to get an undefined y value. And also, same thing here. Notice that you could plug in any x value in this bracket, and sine of anything is always going to give you a valid y value, or a valid output, right? Because sine of x has a domain XCR. If we think about that parent function, basically sine of anything is going to give us a defined y value. I shouldn't say of anything actually, like it depends what expression is here. If, for example, let's say we had an expression x plus 1 over x, well, then there's going to be a restriction. Because notice that that x value can't be 0 here, because there's going to be a denominator. But this x plus 1, if we just look at that, that's just a line. There's not going to be any x value that's going to make that undefined, that bracket undefined, and sine, if that bracket can't be undefined, then sine of anything that's going to be defined is going to give you a defined value as well, right? Hopefully you got that. I know a little bit confusing, but point is that f of x is continuous for XCR, for all x values. And that's good because we don't have to worry about what kind of interval we're going to be picking. We could pick negative x values, positive x values. Any x values that we pick are going to be fine because this function is going to be continuous on any interval. Okay, so that's the first point I wanted to make. So what are we doing? Well, what we got to do is pick two x values that are going to have a negative y value and then a positive y value. And then we'll know that at some point, this function has to cross this x-axis. At some point, this function is going to equal 0. If we find a negative y value and a positive y value. By this theorem, it's going to have to cross at some point. So let's do that. So what we got to do is sort of do trial and error, plugging in x values into this function. Make sure your calculator is in radians. I want to make that note as well. Right? This bracket here is going to be in radians. So you got to do trial and error, picking x values where you're going to get a negative y value and a positive y value. And depending on the function, that may actually take you some time sometimes. But you can also do something. Depending on the function you're given, you can sometimes look at it and know that a certain x value will give you, you're guaranteed to get a negative y value and then a positive y value, respectively. The way you can look at this function here is, notice that sign of x plus 1, this expression here, it's always going to be in between -1 and +1. Right? If you remember, I've mentioned this before, sign of anything, as long as that anything in the bracket is defined, sign of anything or cos of anything, it's always going to be between -1 and +1. So the minimum value that this bracket can take is -1, and if it takes that minimum value, what that means is that you're going to end up with -1 times -2, which would give you a +2. And if it takes the maximum value of +1, +1 times -2 is going to be -2. So what that means is that this entire expression in the function, the maximum value that this entire expression could take, this -2 sine of x plus 1, the maximum value is +2, and then the minimum value is -2. And so all you have to do is pick some kind of x value for this expression that's going to be greater than +2, where this whole expression is going to be greater than +2, because if it's greater than +2 and worse comes to worse, this expression takes its minimum value. Something greater than 2 minus 2 is still going to be positive. And you want to pick some kind of x value that's going to make this expression less than -2. Because if you pick that x value where this expression, x minus 5 to the power 3, is going to be less than -2, and worse comes to worse, this expression takes its maximum value of +2, something less than -2 plus 2 will still be negative. Okay, hopefully that makes sense. Basically, what I'm trying to tell you is that sometimes you could look at these complex functions and pick x values where you're guaranteed to get a positive y value, guaranteed to get a negative y value, if you just kind of logically look at it from a higher level. Not always. A lot of times you're going to have to go through the trial and error process, pick a bunch of x values, and hopefully land on 2. That's going to give you a negative and positive y value respectively. But a lot of times you could skip that, kind of look at the function from a higher level, and know that a certain x value will give you what you're looking for. So all we really have to do is pick 2 x values where this expression is going to be greater than +2 and less than -2. So, for example, f of 7, if we plug in 7 here, 7 minus 5 is going to be 2, 2 to the power 3 is going to be 8. Right? So with this x value 7, we know this expression is going to take a value of 8. And no matter what happens here, if this ends up taking its minimum value, 8 minus 2 is still going to give us a positive number. It's still going to give us positive 6. And then we could pick a or an x value that we plug in here that's going to be less than -2. So notice that 3 would work, because 3 minus 5 is negative 2. Negative 2 to the power 3 is negative 8. So we'll have negative 8 here for this entire expression. And then even if this takes its maximum value of positive 2, negative 8 plus 2 would give us negative 6. So these two x values, this x value is guaranteed to give us a positive y value. This x value is guaranteed to give us a negative y value. And when you actually plug in those x values into the calculator, remember, make sure your calculator is in radians, you'd get 6.02 for this y value, negative 6.49 for that y value. So if we graph this out, if we show this, I actually don't know how this function is looking, but that's not too important. All I know is at an x value of 3, there's going to be a y value of negative 6.49, so 3, negative 6.49. And then at a y value of 7, there's going to be a positive, or at an x value of 7 rather, there's going to be a positive y value of 7, 6.02. And because I know this function, as we mentioned, is continuous on all x values, it's going to be continuous on this interval. If it's continuous on this interval and it has this point, it has this point, no matter how it looks, at some point it's got to cross here. At some point, this f of x is going to equal 0, meaning that at some point, this function is going to have a real root, which means at some point, the original equation that was written down is going to have an x value that makes that left side equal to the right side. But let's properly state it. So let's take these parameters and then throw it into this theorem. So given f of x is continuous on the interval 3 and 7, those are the two x values that we picked, which it is. As we've stated that, we showed that it is continuous on this interval. And f of a, or f of 3, does not equal f of 7, which it doesn't. Remember, f of 3 is negative 6.49, and that does not equal f of 7, which is 6.02, so that's all good. If n is in between those two values, the n that we're working with is 0. We're trying to show that the function is going to equal 0 at some point. So if 0 is in between f of a, f of 3, f of 7, which it is, 0 is in between negative 6.49 and positive 6.02, then there exists a number c in between 3 and 7, where f of c is going to equal 0. And we're done. So you can say by the intermediate value theorem, you could write out this sentence. We proved that that original equation is going to have at least one real root because we've proved that this function is going to equal 0 at some point. There could be multiple points, but there's going to be at least one point between 3 and 7 where it's going to equal 0. So we proved that that original equation is going to have at least one real root.